Welcome in Tilco Advisors. We empower construction material manufacturers with cutting-edge digital solutions. And now, welcome to our podcast, where we share insights from the world of smart construction technologies.
Today we're plunging into, well, the core operating system of the architecture, engineering, and construction industry, the AEC sector. And this is an industry that's deep in a digital transformation.
It really is. And it's not an optional one either. It's a foundational shift. And it's pretty much all being driven by building information modeling. BIM.
Right, BIM, which crucially isn't just a fancy 3D model.
Not at all. That's the key. It's supposed to be the digital backbone, the shared knowledge resource that guides every single decision, from the first sketch to, demolition 40 years later.
And the reason this data is so critical right now is the parallel rise of artificial intelligence.
Exactly.
We're not talking about simple automation here. We're talking about AI driving generative design, running predictive maintenance models, ensuring site safety in real time. The potential is, well, it's huge.
Limitless, but only if the data you feed it is perfect.
And that really is the mission of this deep dive. We're here to figure out why BIM data, specifically when it's packaged in that standard format, Industry Foundation Classes IFC, is failing.
It's just not meeting the strict quality demands of modern AI algorithms.
It's creating what our sources call a massive semantic gap. You've got this incredible AI power on one side and what looks like perfectly good model data on the other, but they just can't talk to each other.
They're not speaking the same language.
So let's just make sure we're all clear on the terms. BIM is the process, the environment where you create the data.
Correct. And ISC. That's the attempted universal language was developed by Building Smart to be this vendor-neutral, non-proprietary format.
The idea being that data from, say, Revit could be reliably opened in a tool from Bentley.
Exactly. It's the data exchange format, the carrier.
But the third piece, AI, needs that data to be more than just present. It has to be high fidelity, semantically rich.
And computationally accessible. That's the key. If the AI has to guess the intent behind the data, the whole process it grinds to a halt.
The history here is really important. AEC was always, fragmented, document-centric.
And really inefficient. IFC was born out of a real need to break down those proprietary silos and get data flowing reliably. It was kind of the industry's big hope for interoperability.
And it did work, to a point.
It absolutely did. IFC succeeded in its original goal, which was data exchange and archiving. It's great at capturing human-readable design intent.
So you can look at the model and understand what it represents.
Yes. But our sources point out that this very success is kind of the root of the current problem.
How so?
Well, it was optimized for humans to exchange information. It was not designed from the ground up for the deep relational querying, the complex machine reasoning that AI and machine learning require.
So it's focused on the structure of the file, not the structure of the knowledge inside it.
That's the perfect way to put it.
It's almost like we built the world's best library card catalog. It's perfect for a human. But now we're trying to hand that catalog to a machine that needs every single card to have, 5 explicit metadata tags to understand how all the books relate to each other.
And the machine just can't make those leaps reliably. That's the tension. The data is there, but the structure of IFC makes it incredibly expensive computationally for a machine to make sense of it.
And this isn't just a technical problem. This has real financial consequences.
Huge ones. I mean, those industry stats are staggering. 30% of AEC professionals report project delays just from file incompatibility issues.
30%. That's a massive drag on productivity.
And it has a price tag. Data exchange problems, that friction, it can account for 5 to 10% of total project expenditures.
So on a large infrastructure project, that could be tens of millions of dollars.
Wasted. Just because one piece of software couldn't reliably interpret the data from another. It makes fixing this a strategic imperative, not just a nice technical feature to have.
Okay, so if the IFC structure is the problem, what's the solution? What does an AI-ready data set even look like? Our sources lay out a framework of 5 critical pillars.
And if any one of these pillars is weak, the whole thing gets wobbly. The AI will either struggle or just fail completely.
So what's pillar number 1?
Structural consistency. This is the foundation. The data has to follow the schema, period. No weird workarounds, no redundancy. The algorithms need predictable input they can trust.
Okay, and second?
Semantic completeness. And this is, I'd argue, where most models fail. It means All the non-geometric properties an AI needs for a specific task have to be there explicitly.
So not just the shape of a wall, but its fire rating, its R value, its material strength.
Every single property. The AI can't guess.
Third pillar.
Geometric fidelity. This is about the accuracy and, crucially, the topological correctness of the physical geometry. This is non-negotiable for things like automated quantity takeoff or QTO or for guiding a robot on site.
Then there's temporal coherence.
Right, the fourth pillar. Linking the model to time. This is your 4D BIM. The data structure has to handle scheduling and progress monitoring seamlessly.
And finally, the fifth pillar.
Contextual richness. This is about integrating with the real world. Think IoT sensors, weather data, drone scans. This is the absolute foundation for a working digital twin.
That's a really clear framework, but I want to zoom in on semantic completeness because it creates this huge paradox, what the research calls the custom set dilemma.
Oh, this is a massive tension point. So an AI needs a specific piece of data that isn't in the standard IFC schema, like, say, a particular acoustic rating.
Okay.
So the project team creates a custom property set, and attaches that data to the model elements.
Problem solved, right?
Yeah.
For their project, at least.
Exactly, for their project.
Yeah.
But in doing so, they've just undermined the entire goal of universal interoperability.
Because that custom set is like a unique dialect.
It's a completely unique extension to the schema. An external AI model or another company's software has no idea how to interpret it. So you solve a local problem by creating a global barrier. You're right back to data silos, but now they're hiding inside a supposedly universal file.
So a machine can't learn across 1,000 projects because each project is speaking its own slightly different language.
1,000 different dialects. It's not a universal language anymore.
Okay, so let's map these failures to the real world. Let's start at the beginning of a project. Design and analysis.
Right. Think generative design, automated code checking. These apps are hungry for two things: semantic completeness and geometric fidelity.
And where do they fail?
Well, they fail when properties are just missing. If you're running an ADA compliance check and half the doors in the model are missing the clear opening width parameter, the AI just stops. It can't proceed.
Or worse, you get ambiguous data.
Exactly. A door is just labeled with a generic tag like IFC building element proxy instead of if door. The machine can't reliably figure out what it is, so the code checker is completely useless.
Okay, let's move into the next phase. Construction management. Scheduling, safety monitoring.
Here the priorities shift. You need temporal coherence and contextual richness. And the failure point is often in the 4D link. Research shows it's really hard to reliably pull time-based parameters directly from an IFC file.
So the 4D link is often a manual process.
It's often forced back into the system by a project manager who is essentially doing the AI's job for it.
And for something like predictive maintenance.
You need that contextual richness. You have to fuse the static BIM data, like a walls material, with a live data stream, like a sensor tracking a worker's location. If the schema can't handle that fusion, the system just breaks.
And what about the final phase? Facility management, energy modeling, digital twins.
Here, a really common point of failure is, believe it or not, the space boundaries.
The shape of a room, that seems so basic.
You'd think so. But energy simulation models need a perfectly closed volume to work. And in IFC models, the boundaries of rooms are often just not accurate. They aren't topologically closed, or they're not correctly mapped to the walls around them.
They have tiny gaps.
Tiny gaps, or the link between the space and its bounding wall isn't machine readable. So the person running the simulation has to go in and manually fix or even completely rebuild all the spaces. It makes the whole automated process pointless.
We've talked a lot about semantics, the meaning of the data. Let's do that deeper dive into the geometric fidelity itself. This isn't just about meaning. It's the raw input for calculations.
It's a critical distinction. For an AI, the geometry has to be mathematically perfect. Now, IFC often uses what's called boundary representation, or BREP. It's a very precise mathematical description of an object's faces, edges, and vertices.
But you're saying errors creep in during translation. What does a catastrophic error look like to a machine that a human would never even see?
One of the worst is non-manifold geometry. This is where the solid is just mathematically impossible. Think of two cubes sharing just a single edge, or a surface that folds back and intersects itself.
So it's not a solid.
It's not. And when an AI tries to generate a mesh for structural analysis on that object, it just fails instantly. The math doesn't work.
And then you have the microgaps.
The infamous gaps and overlaps. We're talking about numerical errors small as in a millimeter, totally invisible to the human eye, But for an automated QTO model that relies on precise boundary intersections, they are absolutely lethal.
Give us a concrete example. What's the real-world cost of a microgap?
Okay, imagine a QPO model calculating the volume of sealant needed between two big precast concrete panels. If there's a tiny, invisible gap between the digital elements, the algorithm might calculate the volume as 0.
So the procurement system doesn't order any sealant.
Exactly. And now your entire project is on hold, waiting for a single box of material, all because of a rounding error in the export process. That's where that 5–10% cost overrun comes from.
And what about orientation? You mentioned flipped face, normal vectors.
Yeah, for things like computer vision or robotic navigation, the direction a surface is facing, its normal vector, is critical. If those vectors are flipped or inconsistent, a robot's perception system gets confused. It might misidentify an object or fail to navigate a path on the job site.
This all sounds incredibly complex to process. So the goal isn't just perfect geometry, but computationally efficient geometry. This brings us to topological fidelity.
Right. We have to be able to shift from that dense, heavy geometry to a sparse, graph-based model. Think of an electrical system. An AI doesn't care about the precise 3D shape of every inch of conduit.
It just needs to know which panel connects to which switch connects to which light.
It's a network, a graph. It's all about relationships and adjacency. The AI can analyze that exponentially faster. But that abstraction only works if the underlying connectivity in the source IFC file is absolutely flawless. If the digital pipe isn't mathematically connected to the digital valve, the whole graph model falls apart.
It's clear the current workflow is full of these landmines. So how do we start bridging this divide? What are the solutions?
The most promising approach right now is converting the data structure itself using knowledge graphs, or KGs.
So instead of that rigid, tree-like IFC structure, you get a flexible web.
A web-like network, exactly. And this is how you solve that custom set dilemma we talked about. A knowledge graph makes relationships explicit.
How does it do that?
It uses standard ontologies, a bit like a dictionary for machines. So instead of an AI having to guess that a custom set called Project Alpha Fire Rating means the same as the standard set fire rating.
The knowledge graph acts as a translator.
It's the semantic middle layer. It provides a universal interpretation layer. It says, regardless of the name, this piece of data is the fire rating. It immediately smooths over those inconsistencies and ambiguities.
This sounds like the industry needs to standardize the translation layer, not just the file format itself.
That's the strategic shift. If we can agree on the ontology, the computational interpretation, then KGs become the universal translator for every AI application.
So what does the ideal workflow look like? We hear about OpenBIM. It's more than just IFC.
It's a whole feedback loop. IFC is still the carrier. But before you export, you need IDS, the Information Delivery Specification.
IDS is the quality gate.
It is. It defines the specific machine-readable requirements. So the IDS might say, every structural column must have a material strength property defined. If it's missing, the authoring tool flags it or just blocks the export.
It enforces quality at the source.
Exactly. And then once the file's out there being used, the final piece is BCF, the BIM collaboration format.
And that closes the loop.
Right. If a coordination tool finds a clash, a data error BCF packages that issue the viewpoint, the comments, and sends it directly back into the original authoring tool, like Revit. So the author can fix the actual source data, not just a downstream copy.
So strategically, what's the big move the industry needs to make?
We have to define minimum AI data requirements, or MADR. This pushes us beyond the vague idea of level of detail, LOD, which is mostly about geometry.
To a very specific level of information need, or LON.
Precisely. MADI would create standardized, domain-specific sets. For example, a universal set for safety analysis, or one for energy analysis. It standardizes the semantic information machines need.
And we need better tools. We can't keep relying on humans to check all this.
The future has to be in automated semantic enrichment, using ML or even LLMs to infer and fill in missing data. And critically, we need robust geometric validation and repair tools.
Automated spell checkers for 3D geometry.
That's a great way to think of it. Tools that can find and automatically fix non-manifold geometry and those catastrophic microgaps before the data ever leaves the designer's computer.
So we've covered a huge amount of ground. The digital transformation in AEC hinges on BIM data, but the current IFC standard is just not ready for scalable AI. It's hampered by semantic ambiguity and these fatal geometric flaws.
And the path forward has to be a unified one. Industry-wide standards like Mayday, semantic middleware like knowledge graphs, and next-gen automated repair tools. We need to ensure all 5 of those pillars, Consistency, completeness, fidelity, coherence, and richness are solid.
So what does this all mean for you? The whole discussion around AI readiness really suggests the focus has to shift. We need to stop focusing on just standardizing the file format and start standardizing the ontology, the computational meaning we layer on top of that data.
When the industry agrees on how a machine should think about a wall, not just how to export a wall, that's when you unlock seamless AI integration.
And the provocative thought to leave you with is this. If the data you're creating today isn't truly machine interpretable, what knowledge layer currently sitting outside your models will you need to define and enforce tomorrow to secure your competitive advantage?
That's it for today's episode. We hope you enjoyed exploring how digital workflows are transforming the construction industry. Don't forget to subscribe and join us next time for more insights into building smarter. Looking for more knowledge and inspiration? Head over to our website. You'll find everything you need to keep building smarter.